The exam is on Wednesday, the first exam. Yeah, it's going to be good to finally get after one. All that training, get to show what we know. I don't get to. Well, I have to do the solution, so in that way I get to. Okay, what? Yeah, after the first exam, I'll give you the first one. So yeah, the first one's coming up soon. So it's this Wednesday. What's that, the 10th? And the topics are through last Wednesday. Which I believe is all the way through particle kinetics. The assignment I'll give you for today is just going to be my best effort to give you a good approach to studying for it. Some notes to skim, and then basically working through all those old problems. Yep. It depends on the question, so I don't know, but it's 50-minute test is, it can't be very many, or they can't be very long. But I definitely will make an effort to make it, I'll try to make it a test where half the class hands it in early. That's going to be my goal. I'm not going to try to make you race against the clock. I'll do my best at that. Sometimes I get it wrong, but I'll do my best about that. Any other questions about the test?
Is it like curved, as in like the top score is the A is 100%? And then
Well, no. So the only thing that is curved possibly is at the end. All the raw scores will be curved if they're too low. And I'm doing the quizzes for the first time this semester, and those scores I think are bringing scores down a little bit. So it's possible. I don't normally have to curve anything, but I think it's looking possible that this class will get a little bit of a curve at the end. We'll see, But the scores are just scores, and then at the end, if nobody, like for example, if nobody's over 92%, then I'll curve it so that what I consider to be a reasonable number of people get A's, a reasonable number of people get B's. That's all I'll do just at the end. I think one change I'm going to make starting after the exam is on the quizzes. I'm going to start. So right now the quizzes are just all on problems that I haven't posted solutions to. I'm going to start making the assignments also involve reviewing old problems that now you have seen the answers to. So the quizzes will be split 50-50 between problems you haven't seen solutions to and problems that you already went through not having the solutions, and now you can correct what you're doing. I just want to make sure that people feel like they understand what they're doing on these problems. Okay, and then after the exam, I'll give you the first problem set. Those will always be just one or two problems. They won't be super time consuming, but they'll be each problem will be considerably more time consuming than like an assignment problem or an exam problem. It's going to be more involved than those, but it won't add like I don't think if you sort of follow what we've gone over, they won't add they won't add 10 hours or anything like that. Any questions about any of that? All right. I'd like to do, let's do 2 example problems today. So for the first one, let's say that we have one of these block and tackle systems. So pulley, 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 and these are connected. And let's say that this is 200 kilograms. That's supposed to be vertical. Oh, and let's connect this to another mass, and let's say this one's 100 kilograms. What's the acceleration vector of the 200 kilogram mass? Okay, see if you can work through this together. Let me know if you get stuck on anything, and I'll go through the solution after you have a little time. Okay. So let's ease into it. Do the easy one first. So free body diagram of the 100 kilogram mass. We have 981 down, tension up, and so Newton's second law says 0t plus 0 negative 981 is equal to the mass times the acceleration. For now, I'll just call this 0 A100. And then the free body diagram for the 200 kilogram mass. And the pulleys. There are cables coming out of those 4 spots, and I think I mention this every once in a while, but as these get more complicated, sometimes I think it becomes more helpful to imagine including a little chunk of cable for any place that the cable is leaving the isolated body. Just isolate a little bit of that cable too, and then the force applied by that cable just comes right out of the stump, so it's easy to get the directions. And then we have 200, so 1962 is the force going down. And then the free body diagram, Newton's second law says 0t plus 0t plus 0t plus 0t plus 0, negative 1962 is equal to the mass times the acceleration vector, and we only have an acceleration in the y direction, so I'll call that a200. Okay, can we solve this? Well, you can count up the equations and variables. In the first one, we only have one useful equation, and we have two variables. In the second one, we have only one other useful equation, and we add a third variable. So we have two equations, three variables, and we can't solve it yet. So what's the key thing that we need here so we can solve it? Yeah, we need one more equation, and where is that going to come from? That's right. That's going to come from that geometric constraint that says, so we can't solve it yet, but the acceleration of the 100 is equal to negative 4 times the acceleration of the 200. And now we can set this up as a system of equations. The first one says, so I'm just going to replace the 100 with 4 times the acceleration, negative 4 times the acceleration of the 200. So t minus 981 is equal to 100 times negative 4 a200. That's just the y component, right? That's just taking the y component here, but I've substituted in negative 4 a200 for a100. Who has a question about that one that they'd care to vocalize? Whatever the 200 is the one that you have to pull a lot on the 100 to make the 200 go up a little bit. You know what I mean?
Right. 4 times the mass.
Right. So, if the 200 goes up 1 inch, the 100 goes down 4 inches.
Oh, yep.
And so we can write this as t plus 400 a200 is equal to 981. And then the second equation says 4t minus 200 times a200 is equal to 1962. And now we have two variables for two equations for two unknowns. You can set that up as a augmented. I mean, that's a pretty easy one to just do by substitution. But I just do it always like this. So we have a matrix where the first column represents the coefficients for t. The second column represents the coefficients for a200. The third column represents the constants on the other side of the equation. And then the first row is the first equation, the second row is the second equation. So for equation 1, t's we have 1, a200s we have 400, and constants we have positive 981. For the second equation, t's we have 4, a200s we have negative 200, and constant is 1962. And now if you do your calculator as the reduced row echelon form function. Do it on this matrix. Call that M. Do reduced row echelon form on M. You're going to get a matrix out that's 1, 0, 0, 1. That doesn't help you at all. But then it's going to give you the answers in order in the last column. So it'll give you the value for T, the value for A200. Can someone punch that in?
545 and 1.9.
Okay, so this is the answer for T, and this is the answer for A200. Does the sign of T make sense? Cable tensions can only apply forces in one direction, and that's the one we drew on our free body diagrams. So if you ever get a negative sign for a tension value, that you better at least look back and figure out why that is, because usually that tells you that your answer is wrong. Okay, so the last step is I asked for the acceleration vector of the 200. This is just a variable value. So now we're going to take this variable value, plug it back into the acceleration that we already expressed, and we get that the acceleration of the 200 kilogram mass is 1.09 in meters per second squared. It's, well, because of the crazy, that's pulley advantage. It's a crazy thing. Like, yeah, it seems like it should be going down because it's heavier than the 100 kilogram. But because of the way we rigged these up, you have pulley advantage, and the 100 kilogram mass is actually going to accelerate the 200 kilogram mass up pretty fast. It's pretty cool. If you ever want to see how it works, if you ever catch me over in 1324, there's pulleys in there and masses, and we can rig this up really fast, and you can see how once you string up these pulleys this way, the lighter mass lifts the bigger mass. It's pretty cool. And they use this in for any shipyards and train depots and whatever, whenever they have to lift big weights, they use this system. The downside is usually you're not just trying to, so if we were just holding on to this rope, if we didn't have the 100 kilogram here, we're just holding on to it and trying to keep it lifted, trying to keep it static, you get this big advantage because you can, you'd be able to hold up a 200 kilogram mass by only exerting a quarter of that weight. But usually you're trying to actually lift it or lower it. And the drawback is that the downside is that for every, like we were saying before, for every inch you want to lift this thing, you have to pull this down 4 inches. If that wasn't the case, you'd violate conservation of energy because you'd be doing more work on this than you were putting into the system here because it's less force. But the works end up being the same because your displacement is bigger even while your force is smaller. Okay. So now we got this thing. copy it down the page with your electric pencil. Okay, so now this is supposed to be like a UFO. And somehow they use this to power it. I don't know. It's alien technology. So now, same question. But the UFO is accelerating up at 5 meters per second squared. So again, you want to calculate the acceleration of the 200 kilogram mass. But now you have to deal with this acceleration of the acceleration of your coordinate system. Okay, so let's first deal with the right sides. Of Newton's second law. So the acceleration vector, well, in either case, the acceleration of the mass relative to the ground is equal to the acceleration of the mass relative to the UFO plus the acceleration of the UFO relative to the ground. And so the acceleration of the, well, we know this one is 0, 5. And the acceleration of the 200 relative to the UFO, we'll call that 0 A200. And so the total acceleration of the 200 relative to the ground is equal to 0 and then 5 plus A200. And then the acceleration of the 100 relative to the UFO is equal to 0, negative 4 times A200. And so we get that the acceleration of the 100 relative to the ground is equal to 0, 5 minus 4 A200. And now the free body diagrams look exactly the same. I'm going to do it anyways because I can never write a Newton's second law without a free body diagram. So we have the weight of 981 and the tension up. And so Newton's second law says 0t plus 0 negative 981 is equal to 100 times 0, 5 minus 4 A200. And so our first useful equation says T plus 400 A200 is equal to 1481. And then the free body diagram of the 200. Yes. For the 200, we have the cable forces acting up. And the weight force acting down. So Newton's second law says 0, I'll lump all these together, 0 4t plus 0 negative 1962 is equal to the mass times the acceleration that we got before, 0, 5 plus a200. And so our second useful equation says 4t minus 200 a200 is equal to 1, wait, what's that? 2962. And so I'll write out this augmented matrix. Well, let's count up, but it should work. So we have the variables are t and a200, two variables, two equations, so it should work. First column is t, second column is a200, third column is the constants, and then first row is equation 1, second row is equation 2. So t's, we have 1. A200s, we have 400. And the constant, we have positive 1481. And then for equation 2, t's, we have 4. A200s, we have negative 200. Constants, we have positive 2962. And if you do reduced row echelon form, you get 1, 0, 0, 1. And then, can someone solve that one? 823? 1.65. Pretty interesting. I was hoping it would be cool, and it was. Yes. So that's the new tension, which is higher like you would expect. That's A200. And so the acceleration vector of A200, we just plug that back into the expression we have. Oh, no, no, no! Oh, we haven't. I don't know. Okay, let's see. So it's going to be, so the acceleration of, the acceleration of A200 relative to the ground is going to be 5 plus A200 in the y direction. And so you get 6.65 meters per second squared. The tension increased, and the acceleration was more than just adding that 5 meters per second squared to the acceleration from the first problem. Pretty awesome. Any questions about that approach? So the key is what you need to do. When you use Newton's second law, you need to make sure that the acceleration you put in Newton's second law is calculated in an inertial reference frame. And so we had to use relative motion to come up with the expression for the acceleration that we put into Newton's second law. Okay? That's why you couldn't just do it in two pieces independently and then add the two answers together. You know what I mean? Okay. Well, exam 1 on Wednesday.